Good morning and welcome to Science in the AM. Science 9. Anyways, just a quick review of what we have looked at so far, and you should have in your notebook. I'm going to flip back. The idea you should write down for developing models of matter is that a theory is a generalized explanation of observations or events supported by research and good arguments. Write that down in your notebook. You guys already have it down, but this is for the recording. So, a theory is not just a hunch or an idea in science. It is supported by scientific evidence. A theory, in common language, is something entirely different. Here, a theory is well supported. It's not just a hunch or a guess. And a law is something different. A theory does not last for 10 years and then they become a law or something like this. It doesn't. That's not the way it works. A law is a generalized description of something from the physical world under certain conditions. The law of gravity is a good example that people have brought up. And it's a mathematical description and tells you exactly how long it'll take for something to fall. Quite good precision. But it doesn't explain how gravity works. Okay? That or why gravity works. That would be a theory. The law is just what happens. Then we talked about, make sure you have that down, an atom is the smallest part of an element that has all the element's properties. An atomic theory is a theory that explains the nature of matter. And matter is composed of little units called atoms, or atoms, sorry. And this is where we're picking up today. Okay, we're going to read through the rest of this text, and then, of course, you'll have some questions to follow. Different ways of understanding. Constantly changing model of the atom tells us something important about science. In a scientific way of understanding, it's common to break apart, analyze things into their smaller parts, then study the parts separately in great detail. This analytical way of thinking is almost the opposite of holistic ways of thinking, which is common sense in indigenous cultures. In holistic thinking, a part of something only has meaning in terms of relationships to the whole thing. Okay. Fine. Oh, we're going to get to this here quickly. Both ways of thinking, holistic and analytical, help us understand what makes up the physical world. There's specific reasons for choosing to view the physical world through one of these approaches. Scientists aim at developing broad generalizations about the workings of nature, whereas indigenous elders focus on methods to help us solve practical and local problems. So it just depends on what you need. Okay. Now the atomic model timeline here in chart. First, John Dalton. A lot of these guys, European, and we're skipping the whole Greek idea because it wasn't supported by evidence, but a guy named Democritus had this idea of atoms and stuff, and cuttable. But there was no scientific evidence. It was just a good idea that he had, but not exactly science. In the early 1800s, John Dalton thought about it. His model was, all matter is made up of small indivisible particles called atoms. Okay? So far, that's still a good idea. We can divide them now into particles, atoms, into parts, protons, neutrons, electrons, and even those can be separated into other parts we found, in a sense. But that still stands because in chemistry, you can't really take apart an atom. That's physics. Those are nuclear reactions. So, but that's his idea so far in the 1800s. All the atoms of an element are identical in properties such as size and mass. For the most part, that still kind of holds up. We've now found that there's isotopes. More about that a little later. Atoms of different elements have different properties, so that's true. Oxygen behaves quite differently than iron. Atoms of different elements combine to form new substances. I'm sure the chemical formula that most people know is H2O. Hydrogens come together with oxygens in a certain way to form water. Okay, that's cool. Then the next one, J.J. Thomson. I'm going to pause this, though, to update the attendance. Oh. Read more in detail. No. Okay. Pause. to this. J.J. Thomson, also English, 1897, so almost 1900. Each atom is composed of smaller particles, so he figured something out that Dalton didn't know. He had evidence that there is particles inside. He figured that there was a positively charged kind of overall ball or sphere with the electrons scattered throughout it. Sometimes people call that the plum pudding model. And that he used plum pudding, not that we're familiar with that. So like a chocolate chip cookie, except a round ball. The chips are like the electrons, because he had evidence that there's electrons. What is this evidence? Well, Dalton, first of all, go back to this. Dalton considered the ancient idea that each kind of element is composed of a different kind of atom. His work and experiments led him to imagine that atoms were like small spheres that they could have different properties. Okay. And some of the stuff he did, think about this. A liquid like water, we're all familiar with that. What do fish breathe? They breathe oxygen. And if you have a fish tank, you have a few fish in it, you can get away without one of these. But you have a little bubbler at the top if you have a larger fish tank, right, with a lot of fish in it. If you only have one fish, a betta fish in a bowl, as long as you change the water once every few weeks, you're fine. There's enough dissolved oxygen. Anyways, you can dissolve gases in water. And he was thinking, how does that happen? They must have room to fit in between the molecules of water, which you couldn't observe directly. There must be space for the oxygen to fit in, or whatever gas, carbon dioxide, or carbonated water, right? It's called pop if you add flavor to it. Things like that. That was kind of evidence, not just that, but other things. Whereas Thomson had something far more technical. He experimented with electric currents in glass tubes called cathode ray tubes. And that was that picture at the start in the textbook at the start of the chapter. It involved magnets and some electricity and stuff like this. And he was able to cause atoms of all the elements he tested to produce streams of negatively charged particles, called them electrons, later called electrons. Since atoms have no overall electric charge, they must have some positives in there to balance it out. Now we call those protons. He didn't know that yet, but there's his supporting evidence. He didn't just come up with ideas. Now, a guy named Rutherford, a few years after J.J. Thomson, came up with the idea that the electrons are outside and the nucleus is inside. All of the atoms, positive charge, and most of the atoms' mass is concentrated at a tiny point in the center called the nucleus. Electrons surround the nucleus and occupy most of the atom's volume, but only contain a small fraction of its mass. So everything's packed in the center, and then the electrons are somehow outside. He didn't describe how the electrons move or anything. How did he do this? He actually didn't expect this to happen. Rutherford shot positively charged particles at a very thin foil of gold. Gold is good to use because you can hammer it really thin into a foil. And most of the positively charged particles went right through the foil. That was unexpected, like to do like that. Or what was unexpected is about 1 in 10,000 of the charges bounce back from the foil as if they'd been deflected from something very massive and positively charged, the nucleus. Now you can see this diagram. Yeah. For the most part, boom, they would go straight through. But if they got close to this nucleus, it would bounce back, and it would just be just like magnets. Opposites repel each other or deflect. Every 1 in 10,000, you'd see this evidence. That meant most of the atom was empty space, but the positive charge was concentrated in this very small space, the nucleus. It would be like taking Taylor Field or, the football field, right, and putting a peanut inside the center of the field. And that's the nucleus. And the rest of the field is the empty space where the electrons can whiz around. Just to put that into a larger proportion, like same proportion, but a larger visual. 1932, James Chadwick, Rutherford's student, proposed that in addition to protons, the nucleus also contained something called neutrons. They're neutral, no charge. Each neutron in an atom has about the same mass as a proton. Niels Bohr, then. This is the model of the atom that people think of, and it's quite simple. It's been built on since, but it's got some good ideas. So a couple of years later, 1913. These ideas of the atom, by the way, are only about a little over 100 years old. And chemistry and this aspect of chemistry and nuclear physics is really relatively new. Things like speed, distance, and time physics and stuff had been explored quite a bit earlier. Electrons are arranged in specific energy levels around the nucleus of the atom. The maximum number of electrons in each of the first three levels is 2, 8, and 8. Okay, more about that. And when we look at the periodic table, let's understand why. Now, Hund, German physicist, Friedrich Hund, was the first to determine how electron pairings occur. Shown in the Bohr diagrams, we're going to do some of those later on. So other scientists, it's not just one person, it's usually a team. Bohr concluded from his experiments that electrons jump between specific energy levels by gaining or losing energy. Each level can only contain a specific number of electrons. There's some weird mysteries and stuff like this in there. Like you can never exist in between. You've got to go from one level to the other. You can't be like level 1.5. Now, from that, it's been built on, and it's continuing to be explored. The modern quantum mechanical model. It's a mathematical model. It's not as visual as most people would like. Electrons do not exist as tiny points. That's why it's not so visual. Electrons exist in specific energy levels, but they surround the nucleus in an electron cloud kind of idea, if you wish. This is where this idea comes from. And based on scientific arguments and evidence, many scientists concluded that the electron could exist at various distances from the nucleus rather than at specific energy levels, as Bohr originally stated. The chance of finding electrons at a particular distance can be calculated. The probable distance changes depending on the different energy levels Bohr had identified. So it went beyond what Bohr had. And I don't think this is a surprise. Got some questions for you to follow up. Describe basic differences between an indigenous approach to understanding the physical world and scientific approach. Holistic versus individually. Okay, we scanned over that. Explain why scientists want to develop models of the atom. What are key points of Dalton's atomic model? What evidence led J.J. Thomson to believe that atoms of all elements contain electrons? We've skimmed over that, okay? Now it's time for you to get that on paper. And just a second here, so that you have this. Okay. And we're going to explore these things. You're going to do the questions first. Page 154, number 154. I'm going to freeze that and pause the video recording. Okay, you're going to do them right